All right, here we go, our very final section, section 16.8. We're going to pretty much just go through the divergence theorem here. So we've talked about this a little bit before, but the divergence is essentially when we do the dot product of our del operator onto a vector field, and that's our divergence. And it tells us how much our fluid, here they say gas, but really it's a fluid. There's not really a difference between a gas and a liquid. But so a fluid is flowing out of or into a point. The reason they're saying gas is because most of the liquids like water and stuff tend to be pretty incompressible, and they don't really have then a divergence of this. So these are expanding or compressing around a certain point, X, Y, Z. And so here we've got just a little example you go through and do. It's just del dot to that vector field 2xz in the I direction minus xy in the j direction minus zk, z in the k direction. And again, it's just a dot product, so you end up with a scalar, and so you get some scalar little function over here, and you just go through and do those little dot products where del in Cartesian coordinates is in the I direction plus partial derivative y in the j direction plus partial z in the k direction. So just dot those together, do your derivatives, and that's it. Here is a few of them here we can do. I'll do the first one just as a quick little example, but we would do del dot and then x, y, z in our component form. So this will be the partial derivative of x, partial x of x plus partial y of y plus partial z of z. And so each one of those will give us a 1, and then it'll be 1 plus 1 plus 1, and it'll just be 3. And so that would be the divergence in part A. So I'm going to go ahead and pause this for a minute and let you try those next 3 real quick. All right, so there are the answers to each one of those. This was A, this was B, this was C, this was D. Now that I scribbled over them. So anyway, let's continue on here. Here we have our actual divergence theorem. This is if you have some vector field F, and we can essentially measure the divergence or all of the faucets on the inside of the volume, or simply look at the flux through the surface of the volume. Now this is very similar to that Green's theorem that we did, except this one goes, I guess is just a more general case where we can do this in 3 dimensions and things like this. So the idea here again is if we had something like a bathtub, right, we could go through and count up all the water coming in out of faucets. If we looked at all the faucets and say there were multiple faucets or something like that, and we could count all the water that was going into this bathtub, and maybe even the drains for where it's compressing in, or we can simply look at and count up all the water spilling over the edges once it finishes filling up. So we're assuming it's been running forever, so it's every drop that goes in to the whole volume is also going to, if a drop goes in, a drop is going to spill over the edge. So essentially that's what we can do here, is go through and do either one. We can either count up around the outer edge or count up through the whole volume, and you pretty much do whichever one is going to work out and has some kind of symmetry or works better for you. So taking a look here, it says for us to evaluate both sides of this equation, where we're doing we're wanting to essentially find this over this sphere, x squared plus y squared plus z squared equals a squared. And we're looking at that function there that is diverging out. And so we're going to do both of them, and then you can kind of decide for yourself which one turned out to be easier. So taking a look here, if we're doing the outer unit normal one, which is our first one there, we can see that our sphere is x squared plus y squared plus z squared minus a squared, and therefore an outer unit normal to that, you take your derivative of it and you get 2 times x, this right here, 2xyz, 2xyz in component form. That just means 2xi plus 2yj plus 2zk That's all that vector is. And then divided by its own magnitude, which then you end up in making sense. You just have a vector that points the same amount in x, y, and z and is over the radius a to give us it in the normal, so its own length. And so that's pretty much it. So for however far out you are, you're dividing it by that and gives you a unit normal. Then if we dot it with our actual function, which was just xi, this here, right here, xi, yj, zk, you dot them together and it's pretty simple to go through in that dot product, and you ultimately just get this a times d sigma. And therefore, if you just do that integral, it becomes just an integral of a. And if you look at this, this is a, yes, right? Okay, it's just some constant. And then this other part is just an integral over a sphere. And so we end up with 4 pi a squared, which essentially this is ultimately turns out to be a third of the surface area here for this one, for that particular field. But yeah, that integral, you can take that a out in front and do that integral, and it's just the surface area of the sphere then. And so we're just adding it all up over the surface area of the sphere essentially. Okay. And then the divergence version, you go in through and do the actual divergence of the field. As you do that, it's just going to turn out to be 3. It's the same exact one we did right here. It's the same f where we got 3. And so it turns out to be 3, and you just do the triple integral of 3. Now, since we're doing a triple integral, we're not doing the surface area of the sphere, we're doing the whole volume of the sphere. So it's 3 times the volume. That's our actual integral. You bring that 3 out in front, you integrate over the sphere, and you get 4/3 pi times the radius, which is a cubed, and then the 3's will cancel, and you're left with 4 pi a squared. So we're getting the same answer here and here with either method. It turns out to be the same thing. All right, so let me pause for a second and see if there's any questions on that. All right, so let's continue on here. If we look here, we have another one here. We're finding the flux of this function here, where it's outward through the surface of a cube cut from the first octant by the planes x equals 1, y equals 1, and z equals 1. And so instead of going through and calculating the flux of 6 different integrals for each face of the cube, right? If the cube is like this, we'd have to go through and calculate for this face and this face and this face and this face and this face, and then that bottom one. So we don't want to do all of that and go through and calculate them all up. So instead, what we can do is just take advantage of our divergence theorem here. And instead of summing up through all the faces, we can simply sum up the interior here. And so you see we calculate the divergence there of the field, which we should be getting pretty good at now. It's just dot product in those partial derivatives. It just gives you y plus z plus x. And then you come down here and just do a triple integral. Now this is going from 0 to x is 1, 0 to y is 1, and 0 to z is 1, because that's where we're bound here, right? It's in this first octant here, right? And so that's what we're going to integrate over, and then you just integrate each one of them. It's actually a pretty simple integral, right? X squared plus xy plus xz is the first one from 0 to 1, and just keep going on in that fashion, and then you have your other 2 integrals on there, dy, dz, and just keep going in that fashion, 0 to 1, 0 to 1, and plug in and go, and you'll end up getting 3 halves there. And so it actually, instead of worrying about doing all those 6 separate integrals, you can just do it in one, and it actually is simplified down here quite a bit by doing the volume integral versus the surface integral. Again, that's not always the case, and later I'll show you an example where you're going to want to go with the surface integral, and it's simpler than the volume one. Okay, all right, so there's our picture of it again. You have some flux in there, and you're just counting up. You ultimately figure out how much is in there, because again, if we have a source in here, say that this is emanating from inside that volume, then every bit of it that comes out of there has to eventually go and leave out through some surface, right? They're all, if that's going through like the top surface and that's going through that surface there, every line is eventually going to leave out of the surface if we can't compress or I'm sorry, as it goes, because it has to eventually leave at some point. All right, so that's what we're taking advantage of there. Here, I don't know how worth it all of this is, but it's just, again, I think the thing I was telling you about is better than what's here. Just components of the vector. Yeah, I'm not a big fan of this whole explanation here, so I'm gonna kind of go right through it here pretty quick. And we're gonna get to this. This is actually the next one I wanted to get to. This one's really interesting. So it says, find the net outward flux of the field F equals xi yj plus zk over rho cubed, where rho is just the square root of x squared plus y squared plus z squared, across the boundary region. A squared is less than or equal to x squared plus y squared plus z squared is less than or equal to b squared. So essentially what this is we're looking at concentric spheres. We've got a sphere inside here with a radius of a, and then we have another outer sphere with a radius of, I should have done that in a different color, with a radius of b. And we're looking at the total flux through the surfaces. So what I'm going to do is go ahead and pause this, give you guys a few minutes to try doing this, and then see what you think of the answer. All right, so for this one, we have two concentric fields, and we have a vector field that essentially is just pointing out radially in every direction, right? It's just a scaled version of the ones we were seeing before. So the field is just pointing out radially like this in every direction. So what this means is if I start to go do the flux over the region, so the flux over, flux over D, our region here, it should be 0. Because if we look at this, every bit that enters in here, which has that negative flux, is then exiting over here. And so we have this one enters and it exits. So it's plus on one and minus on the other, and therefore will amount to a total of 0. So we end up with a total of a 0 flux across the whole thing. And if you wanted to, you could go through and calculate the divergence over the, find that it turned out to be 0. So essentially what this is telling us is the amount of flux that is over the surface of a sphere that's centered around the origin is independent of the size of the sphere. Because what we have here is we have two different spheres, one with a radius of A and one with a radius of B, whose fluxes are exactly opposite of each other. Right? One we're counting as entering into our volume, one we're counting as exiting. So one is positive, one is negative, and they're totally canceling each other out. So it doesn't actually matter the size of our sphere as far as what the flux is emanating from that center point. Therefore, what we can do, if we wanted to find this actual flux through a single sphere, right, through one of these spheres, not through both, is we can say, well, our normal vector, our normal unit vector, is just going to be xi plus yj plus zk, and then over that magnitude, so the square root of x squared plus y squared plus z squared, which is just the radius of our sphere. So it's xi plus yj. So this is just like the result we had a couple pages back, over a, right? And so that's our radius of whatever sphere we're looking at. And so F dot in on our sphere, if we dot product these together, xi plus yj plus zk over a cubed here, whatever it is, a cubed, and then we've got, dotted with xi plus yj plus zk over a, that's our n, right? This is going to just equal, ultimately, when you dot these all together, you have x squared plus y squared plus z squared on the top, when you dot those together, over top of a now to the fourth, but x squared plus y squared plus z squared is essentially a squared because the square root of that would be a. So this is a squared over a to the fourth, which is just 1 over a squared. And then if we go to do this integral, right, over our surface, f dot n d sigma, we'll get this 1 over a squared. We can bring that right out in front because it's a constant. And then we're going to integrate over that surface area here, and we end up with 1 over a squared times 4 pi a squared, which will just be 4 pi. So no matter what sphere we look at, any sphere that we put around that origin, that we center at the origin, then is going to have that flux going through it, as long as we are just looking at one of them. Okay, so let me go ahead and pause this thing here and see if you have any questions.